say you have a protein and it's kind of like hanging out. And then this kinase comes along and it takes this ATP and it puts this bulky negatively charged group onto a part of the protein. Booyah, it's like giving the protein caffeine. Now it's activated and it can do its happy dance. So phosphorylation can activate and deactivate proteins, and it can also open up new binding sites. Because you have this negatively charged group that's going to alter how the protein acts and how it looks. But a kinase doesn't just like come along and push a button on your protein's foot. So how do kinases actually do what they do? Let's take a look.
Kinase is an enzyme, and what that means is that it can speed up a biochemical reaction without getting used up itself. And so if you think of like, it doesn't change the beginning or the final products, it just makes the transition easier. So they lower what we call the activation barrier. So if you think of like a rainbow, we have a pot of gold on one side, but you have to get over the top of the rainbow, and the top of the rainbow is really uncomfortable. The enzyme makes it that rainbow shorter. And so often how this does it is by like stabilizing the transition state. So if you think of snapping a stick and how in the middle, when you're in the middle of snapping it, like right before it snaps, it's really like tense and stuff, and uncomfortable. And so the enzyme makes that easier. And so I want to show you how the kinase can make this an easier transition. So let's look at what we're adding. So we're adding this phosphoryl group, and we can add it in a few different places. So different kinases specialize in adding to different amino acids in different locations. So they'll often have like consensus sequences, or like sequences they like to phosphorylate, and then they'll phosphorylate within that. They'll phosphorylate with somewhere within that sequence, and so. But they'll only phosphorylate on certain residues, so certain amino acids. And so these are tyrosine, serine, or threonine. So typically you have like a serine, threonine, you have a kinase that can like phosphorylate serine and threonine, and a kinase that can phosphorylate tyrosine. And then you might have, there are also kinases that can phosphorylate histidine sometimes, especially in like bacteria. So we have our protein substrate, and it has a phosphorylatable amino acid on it. So it has an OH group that can have a phosphate group added onto it. And then we have ATP. So ATP is going to be the source of our phosphate group. So you might remember ATP. We talked about it before when we were talking about how it's used as a form of energy storage. But here, so because ATP is this form of energy storage, when we phosphorylate things, we can say it like takes energy. So often phosphorylation of proteins is sometimes used as a sort of confirmation step, or something like you're investing energy in this. So you're like investing energy in a certain pathway, and that might devote you to going down that pathway. You see that a lot in metabolism, so the making and breaking of molecules. So let's talk about how a kinase is going to help with this. So we talked about how enzymes can kind of stabilize that transition state, and the transition state here is going to involve some negatively charged, awkward ATP bent type thingamabob. And so since you have this negatively charged thing, you want to help hold it in place and stabilize it. And so to do that, you can use positively charged things. And so kinases often use metal cations. So a cation is a positively charged thing. So often kinases use magnesium cations, which have this +2 charge. They can help hold that phosphate, that ATP group in place. So now you need to somehow get that end phosphate group off. So we call that the gamma phosphate. And we need to remove this. And so how do we do this? So it might not seem obvious because we've talked about how the phosphate group is negatively charged, but that's just the phosphate group overall is negatively charged. And it turns out that charge isn't shared fairly. So the reason why things are charged is because they have an imbalance of subatomic particles called protons and electrons. And so protons are positively charged, electrons are negatively charged. So if you have an imbalance, you're going to have a negative charge. So different atoms, so different elements like carbon, oxygen, hydrogen, they have different set numbers of protons. So an oxygen is always going to have 8 protons, and a hydrogen is always going to have 1, but they can have different numbers of electrons, and they have this ideal number that they want to get to, and so it's oversimplified here, but you can have there's the shell model that helps explain things, and so you have this outer ring of valence electrons, and so atoms want to have that full outer shell. Atoms can kind of join together and share pairs of electrons so that they can each get to their ideal number. And so when oxygen does this, oxygen is really what we call electronegative. It's a total hog. So even it's supposed to be sharing electrons with something, it's going to pull them closer to it. So that oxygen is going to be more negative. So so electrons are these actual things, but they're not really in these rings, they're in these cloud. And so you can think of the cloud being the electron cloud, this negatively charged cloud, is hanging out more by the oxygen than what the oxygen is bound to. And so in the case of the phosphate group, what you have is this phosphorus group surrounded by these oxygens. And so the oxygens are pulling the electrons away from the phosphorus. And this makes the phosphorus partly positively charged, even though it's surrounded by this negative charge, and you might not think that it would be positively charged. And this makes it act as an electrophile. So an electrophile is something that it wants something it wants more electrons. So it's something often positively charged or partly positively charged. And then we need to have if we want to attack it, we can use the opposite. So we need something that has more electrons than they want. And so this would be what we call a nucleophile. So a nucleophile, it's nucleophilic. It loves the nucleus because the nucleus is where there's positive stuff. So it's often negative. And so often what happens is you have an O- group is a really good nucleophile because it has these lone pairs of electrons, and it has so it has more electrons than it wants. So even oxygen, although it likes electrons, it doesn't like being negatively charged. Things don't really like having a negative charge. It's uncomfy. So the oxygen wants to be comfy. And so in order to do this, it wants to find someone to share those electrons with. So it's going to look for something electrophilic. And now let's go back to our kinase. So we have that phosphate that's electrophilic, but we need to get our substrate to want to attack it. So right now we have an OH group. So that's on your serine, your threonine, or your tyrosine. It has this OH group. And an OH group is pretty happy. It's not really, that oxygen's fine as it is. But an O- group, remember, that's going to be really nucleophilic. So we need to turn it into an O- group. So we need to steal that hydrogen. And so often this is usually done with the help of an amino acid that's sticking out into the active pocket. So the place where the stuff is going to happen. So there's often a basic amino acid that is going to pull off that proton. So pull off that H plus and leave this O-. And then that O- can act as a nucleophile. So it's going to attack this gamma phosphate, breaking the gamma phosphate beta phosphate bond. So we just, instead of numbering these, we use Greek letters, so alpha, beta, gamma. So the gamma one is the one that we're ripping off. And so when that O- attacks that bond, is going to rip off the phosphate, but you get this awkward intermediate. So basically there's a little bit of a reshuffling that happens because you attack that end phosphate, that end phosphorus but then that has too many bonds to it, so then it breaks off with the phosphate group next to it. And so you can see that you have an oxygen and it's attacking like this phosphorus. So you're taking 3 oxygens from that phosphorus, so that when we say we're adding a phosphate group, that's why we're actually adding a phosphoryl group, because we're not adding the 4 O's, we're just adding 3 O's. But normally we just say we're adding phosphorus. Like we say that a kinase adds a phosphate group. And then at this point, you can then release the product. So you have a phosphorylated protein and then you have ADP. So now your protein might be changed, and it can do different things. But this isn't necessarily a permanent change, because there's also enzymes called phosphatases that can actually remove the phosphorylation.